Welcome to fascinating world of beams. From towering skyscrapers to sturdy bridges, beams are essential to modern architecture.
What exactly is a beam? Beams are structural elements that primarily carry loads and resist bending. They are typically horizontal or sloped and support weight from above, distributing it to vertical supports like columns or walls. Types of beams. There are several types of beams including fixed beams, securely supported at both ends allowing no movement. Cantilever beams, fixed at one end and free at the other. Simply supported beams, rest on supports at both ends. Overhanging beams, supported at one or both ends but extend beyond their supports. Materials of beams. Beams can be made from various materials such as steel, wood, and concrete.
Fun fact, the Eiffel Tower's unique design utilizes beams to withstand wind forces, showcasing the importance of engineering in architecture.
Beams are crucial in construction, providing support for roofs, floors, and bridges. Without them, structures would not be safe or stable.
Time for trivia question. What material is most commonly used for beams in modern construction? A. Steel, B. Wood, or C. Concrete? Take a moment to think. And the answer is A. Steel. It is a high strength to weight ratio, makes it popular choice for structural applications.
When beams are subjected to loads, they go through different stress stages. At first, they are in the elastic stage, meaning they can revert to their original shape once the load is removed. As the load increases, yielding starts. When the entire cross-section yields, a plastic hinge develops. This marks a crucial point. If the load surpasses this threshold, the beam will fail. A fundamental aspect of beam design is the plastic moment capacity, which is the moment needed to create a plastic hinge. This is determined using the plastic section modulus and the yield strength of the steel.
Pin-ended column with a yield strength of 275 Newton per millimeter squared, 4 meter long is subjected to axial permanent load of 350 kilonewtons and variable load of 300 kilonewtons. So, the design load equals 1.35 times 350 plus 1.5 times 300, which equals 922.5 kilonewtons. As we mentioned earlier, the first thing we need to do is estimate the compressive stress in the column. Let's say 100 Newton per millimeter squared, and evaluate the approximate area required. Hence, approximate area equals design load divided by estimated stress, which is 922.5 times 10 to 3 to convert to Newton, divided by 100 Newton per millimeter squared, and that gives us 9,200 millimeters squared. We need to convert this to centimeters squared. To do this, we divide 9,200 by 100, and this gives us 92 centimeters squared. Then, we need to select a suitable column section size from the table, and evaluate the non-dimensional slenderness. Let's try 254 by 254, 89 kg per meter universal column, which has the following properties. To evaluate the non-dimensional slenderness, we need to use the following equation. Therefore, slenderness ratio equals 4000 mm divided by, open bracket 86 times 6.52 centimeters, close bracket. Let's convert 6.52 centimeters to millimeter. So, it would be 86 times 65.2. Our result is 0.713. From the design curve we should be able to obtain the reduction factor as we get a non-dimensional slenderness of 0.713. If we extend the line to meet at this point with the curve, this gives us approximate figure of reduction factor x which equals 0.7. As a result, buckling stress equals 0.7 times steel strength 275 Newton per millimeter squared. This gives us 192 Newton per millimeter squared. Finally, we need to work out the actual stress which equals design load 922.5 times 10 to 3, divided by area section 114 centimeters squared, divided by 100 to convert it to millimeter. This gives us 81 Newton per millimeter squared. The above column would be safe, but not very economic as the loads produce a stress, which is less than half the compressive strength of the column. It is worth trying a smaller section in this case. You should try 203 by 203, 46 kg per meter universal column and comment below with your findings.